I'm Dr. Mike Murphy. I earned my PhD in computer science from Clemson University, and I teach computer science and information systems at Coastal Carolina University, located in Conway, South Carolina. In this lecture, I'm going to introduce the physical layer of a networking system. I'm going to discuss the position of the physical layer at the bottom of the OSI model, introduce the functions of the physical layer, talk about some properties of physical media, and give a few examples of physical layers in use. The physical layer is at the lowest layer of the OSI model. This is layer 1. This is the layer of the conceptual OSI model on which all the other layers are built. In practice, this is also the layer that contains the networking hardware. The remaining layers can be implemented as software layers on top of that hardware. Functionally, the physical layer provides a fundamental base for building a network system. It is the fundamental layer that underlies any network. In most cases, the physical layer is implemented in hardware and primarily consists of hardware. Now, there is a way that we can virtualize a network, and we can essentially simulate a network using a physical layer that's been implemented as software. But for the most part, the physical layer consists of hardware. This layer provides the basic communication channel that two network devices, such as computers, can use to send and receive messages. This layer includes the transmission and reception hardware, as well as the physical link between the devices. The purpose of the physical layer is to transmit bits. Now, in other layers, we may talk about frames and packets and other types of data structures for organizing data that's going to be sent over the network. But at the physical layer, we're concerned only with transmitting bits. And we're transmitting these bits between physical machines, between different devices on the network. And physical layer's job is to take a stream of bits from one device, encode them into a physical signal, send them over a wire or over a radio, and then decode those bits from the physical signal at the other end in order to extract the stream of bits from the signal. It's also important for the physical layer to isolate different electrical or optical circuits from one another. In the case of an electrical circuit, for example, such as with an Ethernet network, a malfunctioning device on one part of the network should not be able to bring the entire network down by means of a short circuit or some other type of electrical malfunction. So the physical layer also needs to perform what's called galvanic isolation, keeping different circuits isolated from each other. Now, there are many types of physical links. We can generally categorize these links into either cabled links or wireless links. A cabled link has some kind of a cable running between the devices in the network. So here I have a couple examples. I have a patch cable, a Category 5 patch cable. This is a type of cable that can be used with wired Ethernet networks, and this cable uses 8 pieces of copper wire to transmit data. Here I have an example of a fiber optic cable. Now, this particular fiber optic cable is actually used more routinely in audio applications than in network applications, but the idea of a fiber optic cable is the same regardless of the application, and that is that it allows us to transmit light through a flexible piece of glass or plastic. Here I have an example of a wireless device. This uses a couple of antennas to transmit data over radio waves. Now, regardless of the type of physical link, all physical links have to take the bits, the actual digital signals or the digital messages that we want to send at a low level, and encode them into some kind of an analog signal in order to be transmitted over the link, and then decode that transmitted signal at the other end in order to receive the original bit stream. The most common type of analog signal that we use for this purpose is an electromagnetic wave. The reason why we like to use electromagnetic waves is that they typically travel at the speed of light through a vacuum, or relatively close to the speed of light through other materials, and so they're fast. Different types of electromagnetic waves can be used. We have electrical pulses over wire, radio signals that can be transmitted through the air, or pulses of light that can be transmitted through a fiber optic cable. It is possible to use other types of analog signals, however. We could use sound, we could use vibration, we could use pneumatics. Here I have an example of two soup cans being connected by a piece of string. We could technically send audio signals down the string as vibrations, and we could transmit data that way. We don't typically do this, however, because the speed at which the vibration moves down the piece of string is much, much slower than the speed that I could send an electrical signal down a piece of wire of the same length. So we'll typically use electromagnetic signals, but it is possible to use other types of signals. Now, conceptually, in addition to providing the hardware, the physical layer also specifies certain properties of that hardware. So things we have to specify include the type of connection. Do we have an electrical connection? Do we have an optical connection? Is this a wireless radio connection? We need to provide specifications for what kind of cable or what kind of radio we're going to be using for the connection. For example, with Ethernet, we're going to specify with the modern Ethernet system that we're going to use twisted pair cabling. With fiber optic, we're going to specify a type of fiber optic cable. With the wireless network, we're going to specify a particular type of radio. We also need to give physical requirements for the connectors, the antennas, and any other attachments that are going to be used with these cables. So for example, with wired Ethernet, we have a standard 8-pin plug that we can utilize to attach different devices to the cable. If we didn't have standard attachments, it would actually be extremely difficult and relatively expensive to connect different devices together. So this layer is highly important. It could be argued, in fact, that the physical layer is the most important layer of any networking system, simply because none of the other layers work without it. This layer defines the communications hardware that's going to be used to implement the network, and every other layer of the OSI model can be implemented on top of it, and moreover, every other layer of the OSI model can technically be implemented entirely in software. So the software needs some kind of hardware on which to run. The physical layer provides that hardware and allows the network to function. So let's look at a few examples of different types of physical layers. In the case of wired networks, we have things such as the Ethernet physical layer for standard Ethernet connections between devices. It's not really so much a networking protocol in practice, although it can be used for this, but the Universal Serial Bus, or USB, does have a physical layer specification. Included in that specification is what a USB connector looks like, how it's shaped, and how it's designed. And this way all USB devices can interoperate with each other because they use the same type of connector, the same kind of electrical specification. Digital subscriber line, or DSL, has a physical layer. Cable modems have a physical layer as part of the DOCSIS standard. And even good old-fashioned dial-up telephone modems had a physical layer as part of the V92 standard. In wireless devices, we have other standards of physical layers. So for example, for Wi-Fi or 802.11 devices, we actually do have a couple of different physical layer specifications depending on the standard revision. Bluetooth specifies its own type of physical layer, as does the GSM Mobile U interface, or the UM interface, for 3G cell phones. And for 4G LTE cell phones, there's another LTE physical layer with its own specifications. Fiber optic also has specifications. For example, wide area fiber optic systems, or SONET rings, have their specifications. And even the combination of optics and wireless with the infrared light-based wireless devices, wireless infrared, or IRDA, has a physical layer specification. So we have these specifications for all of these different types of physical layers, but all of these different types of physical layers share a common purpose, and that is that the physical layer itself, conceptually as part of the OSI model, defines and provides the hardware required to transmit and receive bits over a network link. we have a bunch of different choices of physical layer. Different ones exist for different purposes, including multiple varieties of wired electric, wireless radio, and optical connections. But all of them serve the same purpose, and that is to provide the hardware layer upon which the rest of the networking system will be built. Thank you for watching. For additional lecture materials, please see my website at www.mikemurphycs.com. Please note that due to a high volume of email, I am unable to respond to questions that are not from Coastal Carolina University students. For more information about Coastal Carolina University, including admissions information, please visit www.coastal.edu. This video is licensed under the Creative Commons Attribution Share Alike 3.0 Unported license. For more information, please visit the Creative Commons website. I'm Dr. Mike Murphy. I have a PhD in computer science, and I teach computer science and information systems at Coastal Carolina University. In this lecture, I'm going to introduce the data link layer. I'll be discussing some of the properties and functions of this layer, talk about framing, framing overheads, and collisions, talk about the LLC and MAC sublayers, which are conceptual divisions of this layer into two parts. So the data link layer is the second layer in the OSI model. It's the second layer up from the bottom. It sits on top of the physical layer, and the network layer sits on top of it. And the data link layer is the first layer of the OSI model that's primarily implemented in software. As we said before, the physical layer is typically implemented using hardware devices. But the data link layer is primarily implemented in software. Now, this software could be software running in a standard computer system, but more frequently it's actually software that's embedded in the physical devices themselves, such as the switches, network adapters, other types of network devices. We call this type of embedded software firmware because it's actually sort of built into the hardware, so to speak. It's not really a general purpose piece of software that we would install separately. Now the data link layer has two important functions. It's responsible for transferring data between two devices on the same network segment. So that means if you have two devices that are very near each other, or even two wide area network devices that are directly connected on the same network segment, the data link layer will get data between those two devices. Now it does this by splitting the data into units known as frames. And frames are simply groups of bits that comprise one unit of data along with some header information and some error checking. If we look at IEEE 802.3 Ethernet, for example, we can see that a frame consists of a header of 22 to 26 octets or bytes in length, a payload of 42 to 1500 bytes, and a 32-bit cyclic redundancy check, or a checksum, that can be used to detect errors in the rest of the frame. Now if we break the header down into its component parts, there's a 7-byte preamble, a 1-byte start of frame delimiter, a 6-byte destination MAC address, a 6-byte source MAC address, an optional VLAN tag, which if present is 4 bytes long, and a size field of 2 bytes that tells us the size of the frame. Now, notice that I have this header here. This is a minimum of 22 bytes, and this CRC here, which is a 4-byte or 32-bit checksum. Frame headers and checksums add overhead to the payload to be transmitted. So if I want to send 1500 bytes of data, and I'm going to send it over an Ethernet connection, at layer 2, at the data link layer, I'm going to be adding a bare minimum of 26, possibly up to 30 bytes of overhead to that payload. That means that in order to transmit 1500 bytes, I'm going to have to transmit 1526 to 1530 bytes over the physical layer, because I have to transmit this header and this checksum along with the payload. The payload is simply what we're interested in sending over the network. So that could be the contents of a file, that could be a web page, that could be anything that we want to get from one end of the network to the other. So in order to send any 1500 byte block, I have to have this header and checksum. So that works out to just under a 2% overhead, 26 bytes out of every 1500. And that's without VLAN tagging. It gets a little bit higher if we use VLAN tags. So for every 1500 bytes that I transmit, I have to send at least 1526 at the data link layer through the underlying physical layer. So if we take 1500, we divide it by 1526, we get that payloads comprise about 98.3% of the data sent over the physical layer. So for however much data that I have passing through the data link layer and going to the physical layer, with Ethernet at least, about 98.3% of that is going to be data I'm interested in. The rest is going to be overheads. But recall that we talked in the physical layer about the fact that when we talk about the speed of a link, we are often talking about the physical layer speed. Gigabit Ethernet, for example, gives us 1 gigabit per second, or 125 decimal megabytes per second, at the physical layer. But only 98.3% of that is actually used for the payload. In other words, the data that we're actually interested in sending through the data link layer. So if we were to measure the speed of this link at the data link layer, we would measure it at only about 983 megabits per second, or about 123 megabytes per second. So we're losing a full 2 decimal megabytes, a full 2 million bytes per second over the link, simply because we've added in this data link layer that's adding overhead. And what will happen is if we add a network layer on top of that, which we almost always do, we'll see our effective speed go down even further, because the network layer is going to add additional overhead. And this is just a property of the system. It's a normal and expected property of the system. So what do we get for all this overhead? Well, whenever we have multiple network devices on the same shared medium, now this was the case with original Ethernet when it was a shared bus. These days with switched Ethernet this isn't so much a problem, but it is still a problem with wireless devices because they're sharing the same airspace, sharing the same set of radio frequencies. Two network devices might try to transmit a frame at the same time. If that should happen, the two frames interfere with each other, and the result is a garbled message that neither recipient can decode properly. It's meaningless data for both recipients that were trying to receive the two frames that collided. So the data link layer has to handle collision situations. One of the first things it needs to be able to do is ensure that the channel is clear before trying to transmit. Make sure that another device isn't transmitting before it tries to transmit. This is called Carrier Sense Multiple Access, or CSMA. The data link layer also needs to be able to detect when a collision occurs or have a way of avoiding collisions, either collision detection, CD, or collision avoidance, CA. Collision avoidance is the current standard for most wireless communications devices. Now we can break the data link layer conceptually into two sublayers: the logical link control, or LLC sublayer, and the media access control, or MAC sublayer. The LLC sublayer allows multiple different network layers to share the same data link layer at the same time. It performs something called multiplexing. So it allows different network layer technologies to be used at the same time over the same link. The logical link control layer can also provide some flow control, error correction, message acknowledgement type features, although those are optional. The media access control layer provides layer 2 addressing of devices. So we've said that two devices that are on the same network segment can talk to each other. Well, in order to find each other, they need to have an address. And the Layer 2 Media Access Control sublayer provides such addresses. The MAC sublayer also detects or avoids frame collisions, and it figures out where frames start and end. Remember, the physical layer simply provides us with a stream of bits. It's up to the MAC sublayer of the data link layer to figure out where the frames start and end within those bit streams. So to summarize, data link layer is layer 2 in the OSI model, and it can be conceptually broken into the LLC and MAC sublayers. This layer is responsible for transferring data between two devices on the same network segment, and in the process of doing that, it implements framing and collision mitigation abilities. This layer is primarily implemented in software. However, in many cases, the data link layer is actually implemented in firmware that runs inside network devices. Thank you for watching. For more information, including additional lectures, please visit my website at www.mikemurphycs.com. Due to a high volume of email, I am unable to respond to questions that are not from Coastal Carolina University students. For admissions information, please visit www.coastal.edu. This lecture is copyright 2014 Dr. Mike Murphy and is released under Creative Commons Attribution Share Alike 3.0 Unported License.